Welcome again to Physical Chemistry Lab. Look at electrical conductivity of two different solutions. One, a strong electrolyte, some potassium chloride we're going to use for that. And another, a weak electrolyte, acetic acid, right? So we have over here a couple of different carboy full of acetic acid and a graduated cylinder of, volumetric flask of KCl. And the first thing we're going to do is we're going to take our lab notebook, right, where we're going to write down our data and stuff in here, title, date, right, title and date, and we're going to note that the stock concentration of the KCl is 0.9909 molar. And we're going to note that the stock concentration of the acetic acid is 1.004 molar. We're going to use those to make up our solutions, right? So that the concentrations are a little bit different than what we have in our here. So that instead of making up a 1 millimolar solution to start off with, right? That first one is going to be 1.004 millimolar, right? And the KCl, instead of being 1 millimolar on its lowest concentration, will be 0.9909 millimolar, right? Because there's not exactly 1 molar solutions to start off with, and therefore we've got to multiply our stock solutions there by 0.9909 for the KCl and 1.004 for the acetic acid. All right, so we note that we've got our solutions and we need our conductivity meter. Oh, conductivity meter. It is the conductivity that we're going to measure. And we're going to end up with that in units of, I'm going to give you that in SI units. So when I give you the table, SI units for that one, it's going to be in Siemens, capital S, per meter, right? But note those the concentrations I give you are in molar units, so you want to switch those over to moles per cubic meter, right? Okay, what are we going to do? We are going to use this conductivity meter, right? Which has a probe that looks like this. It's a glass tube, and you'll note there's a glass tube, and inside the glass tube, this is really important, there's a little coil in there, a wire of metal. That is what does the measuring. It's actually on the inside, way up about here. It's not at the end of the tube. It's not on the outside of the tube. It's inside, right about here. That means that when you're doing measurements with this, it's very important that you have to cover the measuring bit, right? So we're going to use a graduated cylinder as our measuring device, right? Because we need to completely cover the measuring part, which is not just the tube on the outside, not the tube at the very bottom, not like this. We need to completely cover it, submerge it in the liquid, right? This is very important, okay? Because the measuring bit is also up on the inside of this tube, right? Conductivity is great because it's sensitive to all ions, not just any specific ion, but all ions in solution. So we've got to be meticulous about cleanliness in this one, right? So it's not okay to simply rinse this guy off, right? Because if you just rinse it off out here, aha, wait a minute, where do we measure? We measure on the inside of the tube up there. So in order to really clean this off, what we need to do is swirl it in a nice big beaker. Look at it, that's a big beaker of water, right? Because we need cleanliness in this one. This is very important. So we need to clean it on the inside, not just the outside. So you can't just rinse it with a wash bottle, right? You need to rinse it on the inside as well. So we'll keep that there, right? We're going to be really careful about making up solutions. When we look at the directions there, we see we need about 30 mLs of solution. Oh yeah, 30 mLs of solution in a graduated cylinder, right? And we're going to be switching these things around. We're going to make up 5 dilutions for each one, KCl and acetic acid, right? And so if we're going to need 30, we could rinse at least once, right? That would be good. And have perhaps some solution left over in case we have to do it again. So let's make up 100 mLs of each one of those. And if I have 100 mLs of solution, then what I can do, right, is I make sure all the glassware was clean in the first place, because you have to be meticulous about using high purity, right? You want no other ions. So what are we going to make our solutions out of? Ooh, we're going to use not just DI water, but we're deionized and then distilled. We use the good water because we have to have the lowest possible background of other ions. And so we're going to wash out our glassware, and to make sure that we get the right conductivity, we want to rinse it with the solution that we have, right, that we're going to measure with. So it's a good idea to rinse that, right? Make sure we rinse that, get all of that to be the solution and only the solution that we want. Instead, we need about 30 mLs. So let's fill this up with about 30 mLs worth. There we go. Good, right? Okay, and then, right, because we need 30 mLs of solution, right, that we used deionized distilled water to get that background down low. And, right, the other thing that we need, that in our, we've got a bunch of solutions there, 5 different ones. We want to make sure we don't cross-contaminate. So not only are we going to clean in between each solution, but we're going to start off with the lowest concentration, right? Why are you going from the lowest concentration? Because you're going to stick this in here. It's all nice and clean up. And stick this in here. We're going to let the reading stabilize. It takes a little while, 10 or 15 seconds for it to stabilize. Then we're going to make that reading. We'll write down our number, right? And then we're going to do that a couple of times to make sure we get the right reading, right? And we're going to do our statistics on that, right? So between, when we're using one solution, right, we don't have to, when we're using one solution, we get that totally submerged like that. We don't need to rinse in between these measurements. We're going to make 5 measurements so that we've got several in there. And we're going to note those all down. But in between solutions, right, we're going to go from one to the next. And just in case, right, because we're going to take this, we're going to grab the next solution, right? We're going to rinse this out to clean it up. We're going to use some of the solution we're about to measure to rinse it, because we want to make sure that the concentration is what it says on the tin, right? So we'll rinse this out a couple of times. Then we fill it up with our solution, enough to completely submerge it, right? And if we were to transfer, unfortunately, a drop of the old solution to the new solution, right? If we're going from low concentration to a higher concentration, then it's not going to show up. But conductivity, conductivity is sensitive to all ions in solution. And if we instead started off with one of the highest concentration ones, one drop of the highest concentration one may have more conductivity in it than the lowest concentration solution altogether, right? So you start low and you go high. You completely submerge it. You wait for this reading to stabilize. Takes a little while. Be consistent. If it's taking 10 to 15 seconds, make sure you take 10 to 15 seconds for each reading. You want to be consistent from one to the next. Great. We do that for all the solutions, right? We're going to make 5 measurements for each solution. We don't have to rinse between those, but then when we change from one concentration to the next, we're going to change solution. We're going to rinse, right, between the solutions. We're going to rinse in a big beaker, and then between the KCl and the acetic acid, we better change that water altogether, right? Because the KCl is a strong electrolyte, has a lot of conductivity, electrical conductivity, than does the weak electrolyte with the same concentration, acetic acid, right? Now, we get that data. that data is pretty, it takes much longer to make up the solutions than it does to make the measurements. It's really easy to make the measurements. And then it asks us to make 2 different plots to analyze this, right? Very important how we do this. One of these, right, for KCl is going to be conductivity versus the square root of concentration, okay, for the KCl. And that's going to look pretty much like kind of flat line with just a little bit of a slope to it. Then we're going to fit a line to that. And we're going to measure the intercept. And the intercept is going to give us the, from the molar conductivity, we're going to get the limiting molar conductivity. Limiting as in the limit of infinite dilution, right? Okay. It's okay to do an intercept like that. This is a really flat line anyway, right? Okay, now the other data, it's going to be 1 over, it's going to be the reciprocal of molar conductivity for acetic acid. Let's call that HA, right? And we're going to plot that versus the conductivity. Conductivity is what we actually measure, right? And there, we're going to get some data that is going to look like a decreasing trend. We'll fit a line to that. And we could get the limiting molar conductivity either from the intercept or the slope. Okay, now there are 2 points that I want to make here, right? In general, right, slopes are a more accurate way of measuring something than an intercept. Why is that? The reason for that is our measuring apparatus, right, might have an offset. It might not be properly calibrated. There might be an offset that is given to it and you just have an offset from the real value. What happens to an intercept if you have an offset? Well, it either goes up or down, okay? Well, if you go on a curve and you go up or down on a curve, you don't, if you add the same offset to all the data points, you don't change the slope. A slope is insensitive to a constant offset. Now, if you have a big value that you're measuring and you have a very small offset, then it's not a big problem with measuring an intercept. So if you have large numbers and small offset, no problem. We can measure an intercept and it should be accurate, right? We've got a very flat line and it's a large value. This intercept is a good way to measure. Down here though, we're extrapolating a line towards 0. And we're trying to measure a value down here. If we have a small offset, but the offset is comparable, oh, wait a second, we're trying to measure a number that is close to 0. It's going to be really hard. This intercept here is very sensitive to offset errors. The slope is insensitive to offset errors. So if we measure a value of the limiting molar conductivity from the slope, it should in general be more accurate than the intercept in this case. Particularly because if we have an intercept near 0 and you have an offset error, the offset is comparable to the intercept you're getting. You might get the wrong sign. And it is unphysical to get a negative limiting molar conductivity. So we don't want to do that. We're going to use the slope in our analysis for acetic acid. We're going to use the intercept because it's a big intercept on a flat line, right? Not an intercept going towards 0. So we can use that for KCl. All right? So that is our experiment for this week, right? Be careful about cleanliness. Know how you're making your experiment work in the lab when you take the data, and therefore what it's sensitive to for interferences, and think about how you analyze your data to analyze it in the best possible way.